Today we will solve the problem 3.37 of Griffith third edition Introduction to Quantum Mechanics. The problem 3.37 is related to Virial theorem. The problem is use equation 3.73 to show that time derivative of the expectation value of x xp is equal to 2 times the expectation value of the kinetic energy minus the expectation value of x delta v over delta x, where T is the kinetic energy and H is equal to the kinetic energy plus the potential energy. In stationary state, the left side is 0. So naturally, if it is stationary, the expectation value of x multiplied by p is equal to 0. That means 2 times the expectation value of the kinetic energy is equal to the expectation value of x, the time, partial derivative of v over x. This is a Virial theorem. Use it to prove that the expectation value of kinetic energy is equal to the expectation value of potential energy for a stationary state of the harmonic oscillator, and checks the consistent with the result you got in problem 2.11 and 2.12. So the equation 3.73 referred in this problem is time derivative of the expectation value of an operator q is equal to I over h cross the expectation value of the commutation of Hamiltonian with that particular operator q plus the expectation value of time derivative, partial time derivative of q. Uh, Normally, this will be equal to 0 if there is no explicit time dependence. We will see in this problem. From the Schrodinger picture, also as shown in the equation 3.37, we know the time derivative of an operator q is equal to I over h cross the expectation value of commutation of Hamiltonian with the operator plus the time expectation value of time derivative of the partial time derivative of the operator. If if there is explicit dependence on time, so now generally it will be 0 because there is no explicit time dependence. So you can take only the first term. Here the expectation value of time derivative of expectation value of q here it is given as x dot p, x multiplied by p, which is equal to I h cross the expectation value of commutation of Hamiltonian with x and p. So using commutation relation, we can expand this commutation relation. First, you take right hand side operator to the right hand side. Then the commutation relation will become commutation of Hamiltonian with the x multiplied by this p. Similarly, the left hand side operator you take left hand side. So left hand side x, the commutation of Hamiltonian with p. Here you replace this Hamiltonian here by p squared over 2m plus v, kinetic energy plus potential energy. Here as well as here you are replacing here. Now you take the first commutation relation. So v depends on x alone, so v and x will commute, so we can remove this v from the first commutation relation. So this will become p squared over 2m, commutation of p squared over 2m with x. Similarly, the second term, the commutation p squared will commute with p, so we can remove this p squared over 2m. then this will become x multiplied by the commutation of v with p. So now we will solve this commutation relations. And now we got this expression. Here we have to solve one by one. That is first this commutation. So commutation of p squared over 2m with x. So here you take constant outside 1 over 2m. This can be written as p squared can be written as p into p. So using commutation expansion, you take the left hand side p to the left hand side, then you will get p commutation of p with x. Similarly, the right hand side p to the right, so you will get commutation of p with x. So p with x is minus I h cross. We will get minus I h cross. This also minus I h cross. So you will get 1 over 2m minus I h cross, already there is p here, and here also minus I h cross p. So if you add these two, you will get minus 2 I h cross p. So 2 will get cancelled, you will get simply minus I h cross p over m. So the first commutation is this one. Minus I h cross p over m. Then you take the second one. So the commutation of v with p, you take some arbitrary function g of x. So this commutation of v with p can be written as vp minus pv. Of course, you remember that there is gx here. So first Vp, V you have taken first, and P you take the operator of P, which is I h cross delta over delta x. Already there is gx here. Then minus PV. Minus PV, you have gx, you have to multiply. So P is equal to minus I h cross. So minus of minus will become plus. Plus I h cross delta V, of course you have gx. V gx over tx. Now you keep first term as it is. Second one you differentiate UV method. So first you keep V as it is and differentiate this gx, you will get this term. Then you keep gx as it is and differentiate v, so you have that term. You take first two term, both are equal and opposite, so this and this will get cancelled. So you can cancel these two. So finally you will arrive at, you remove this gx, here gx. So the commutation of v with p is equal to I h cross delta v over delta x. Now you replace, that is I will erase this. Now you replace this p squared, commutation of p squared, first commutation, p squared over 2m with x is equal to this minus I h cross p over m. So I have replaced this commutation relation. Minus I h cross p over m. Remember that there is I over h cross outside. Then similarly here you replace this commutation vp by this one. So already there is x outside. So you can take I h cross delta v over delta x. Now we will simplify it further. So we have seen this relation. Now we can cancel some of the thing. That is h cross. You can cancel h cross because here it is in the denominator, here it is numerator. Then you have I here, I here. I squared is minus 1, minus of minus will become plus. This will become simply, here you have one p, here another p, p squared over m you will get. This minus will become plus, of course, I have told. Then here, if you multiply this I and this I, you will get I squared, which is minus 1. So the second term will become minus x delta v over delta x. You can see p squared over 2m is the kinetic energy. Then this is 2 times the kinetic energy, because you can multiply and divide by m, 2, sorry, multiply and divide by 2. So then you will get p squared over 2m. So this is 2 times the kinetic energy minus the expectation value. This is expectation value of kinetic energy. Then minus the expectation value of x multiplied by the partial derivative of the potential. Now, for a stationary state as given in problem, for a stationary state, this left hand side will be 0, because if you differentiate the constant with respect to time, you will get 0. That means uh, 2 expectation value of kinetic energy minus expectation value of x delta v over delta x is equal to 0. That is 2 times the expectation value of kinetic energy is this one is equal. Now you bring 2 to the other side. The expectation value of kinetic energy is 1 over 2 uh, expectation value of x and partial multiplied by the partial derivative of v with respect to x. Here, according to Virial Theorem, the expectation value of kinetic energy is equal to 1 over 2 r dot sorry, this is r dot gradient of v. So in 3 dimension, in 1 dimension, this is x dot delta v over delta x. So we have proved the Virial theorem. Then we will continue our discussion further. Now we got this relation. In the case of harmonic oscillator, because we have asked to prove it that kinetic energy is equal to potential energy in case of stationary harmonic oscillator. So V is equal to half m omega squared x squared for harmonic oscillator. If you differentiate this with respect to x, then this x squared will become 2x, 2 will get cancelled. You will simply get m omega squared x. If you multiply by x both side, you will get x delta v over delta x is equal to m omega squared x squared. Now you use this here. If you use this, that is of x, expectation value of x delta v over delta x. So you know this half you take as it is. This term inside the expectation value is that is x delta v over delta x is equal to m omega squared x squared, and you take this off. So naturally this expectation value of kinetic energy is equal to this expectation value of potential energy. From using this, comparing this and this, you will come to the conclusion that the expectation value of kinetic energy is equal to the expectation value of the potential energy. Thank you very much for watching my video and supporting me continuously. Thank you very much.